Alright, let's get started with the hopefully the conclusion of this podcast. This is the 7.5 section, and what we're going to be talking about here is canceling of forces within a system and why forces don't cancel when they're external to a system. So we said the forces are equal and opposite. So you're obviously, you would say, and they're simultaneous. So you'd say, why don't they cancel out to zero? Why don't they cancel each other? They are going in the opposite direction, and they are the same. What we have to first do is look at systems, and you're going to see a dashed line around this orange taking a ride in a cart, and that dashed line represents a system. The orange and the cart are within the system. The ground and anything that might be pulling on the cart are outside the system. So let's just say a force pulls on the orange. Maybe it's a rope outside. The orange and the cart are going to accelerate to the right. So the thing to look at here is that the line comes outside of the system, so it indicates the force is from outside the dotted line system. And if it's external to that system, then it's going, the orange system, it's going to accelerate the orange. It's actually going to have a force on the orange. So now let's take an apple. We'll say that the apple is pulling on a rope and it's pulling the orange. So if you look, the apple is pulling on the orange, that's one force, and the reaction force would be the orange pulling back on the apple. But remember, the reaction force is not operating on the orange, so it's not canceling out the pulling force on the orange. The orange is still going to accelerate. So the force by the orange is outside the system because the apple is outside the system. The orange simultaneously exerts a force on the apple, but it's external to the system, so it does not affect the orange. It only affects the apple. So you can't cancel the force because they are both, one is within one system, the orange, and then the other force is outside the system of the orange. So they will not cancel each other. So in this case, if we consider the system to be the apple and the orange, the forces inside the system will cancel. But if the apple were to push on the ground, the orange and the apple will accelerate together. That this force down here is outside the system. That's the force of the ground pushing back on the apple as the apple pushes on the floor. So when the force pair is internal to the orange apple system, the forces do cancel and they don't accelerate the system at all. That would be this force right here. It's internal to the system, so the forces do cancel. When the force, so a force external to the system is needing for acceleration, and that force is provided by the apple pushing against the floor. The apple pushes against the floor pushes back on the apple. That force is external to the apple-orange system. Alright. Another analogy can be to baseball. If you think about all the interatomic forces within a baseball, they don't really do anything to the baseball. The baseball isn't going to move just spontaneously because of forces inside. They're all going to cancel out. They're within the system of the baseball. So you're not going to see a system accelerate. However, when a force external to the ball, such as a bat hitting the ball is going to accelerate. There's another way to look at it. We're going to add a third object in here. A acts on B, and B accelerates. The force from A is external to the football. But if A and B act on the A and C, both those feet act on the football does not accelerate. They're equal and opposite. So you might say, well, is the force of A on B and the force of C on B action-reaction forces? The kicks are simultaneous, equal and opposite, but the net force is on the ball 0, but they're not an action-reaction pair. Remember, action-reaction pair has to be A on B, B on A. In this case, it's A on B, C on B. So that's not an action-reaction pair. So, there's a little question that says, suppose a friend who hears about Newton's third law says that you can't move a football by kicking it because the reaction force by the kick ball would be equal and opposite to your kicking force. The net force would be 0, so no matter how hard you kick, the ball won't move. What do you say to your friend? Well, what you would say is the ball will accelerate because the only force on the ball is the kick. The force from the ball on your foot is external to the ball. Therefore, the ball will move. And just to summarize, why don't action-reaction forces cancel each other? They do not cancel each other when either of them is external to the system being considered. Alright, here's another problem that actually relates very closely to what we were talking about, external systems. This is called the horse-cart system, and it's not that much different than the apple-orange system. Here we have a horse pulling a cart, and what we're going to see is that the acceleration of the horse actually comes down to, and the horse-cart system comes down to just a couple of forces. The force of the horse being pushed by the ground and the friction of the ground on the cart. The question is, will the horse pulling on the cart's pulling on the horse, won't they cancel each other out and acceleration be possible? So let's look at it from the point of view of the farmer. If you look at just the cart, which is the only thing that the farmer is really interested in, you'll see that there's only two forces on the cart. The pull, P, from the horse pulling on it, and F, friction, the friction pulling back on the cart, the friction of the ground on the cart. So if we take the force on the horse and the mass force of the cart and the mass on the cart, we end up finding the acceleration of the cart. And you've got to remember that the farmer just doesn't care about the horse. He's really carried about what's going on with the cart. So he's looking once again at the pull of the horse on the cart and the friction on the wheel. Now let's look at the horse. With the horse, the force on the cart is pulling back on the horse. That we represent as a big letter P. And the force is moved forward by interacting with the ground. The horse pushes backward on the ground with this big F here, and the ground pushes back on the horse with the big F there. So for the horse, it's big F, big F minus this P right here. Let's look at the horse and the cart system as a whole. What you're going to see here is the pull of the horse on the cart here and the pull of the cart back on the horse are internal to the system. We'll consider this purple circle our system. They're going to cancel each other out. They're not going to have any effect on it. They can be neglected in this case. So what we're then left looking at is that what's left is the push from the horse on the ground and the friction on the cart will determine the horse, whether the horse is able to move the cart. So here's a little cartoon that explains the whole thing. You can see this in your book. It pretty much the whole punchline is about the horse thinking that he doesn't have to move because it's going to make any sense. But anyways, moving on. Let's look at this in summary then. What's the net force that acts on the cart, on the horse, and on the ground? Well, if we look just at the horse, we have the big F here, and let's look at the cart first. We have the pull here, and the friction on the back. For the horse, we have the force of the ground back on the horse, pushing it forward, minus the pull of the cart backwards in the other direction. And remember, direction makes a difference here. And then lastly, the ground, it's the push of the horse going backwards, and the friction, remember these are a pair right here, going forward in the forward direction. So the net force on the cart is P minus F, big P minus little f. On the horse, it's big F minus little p, and on the ground, it's big F minus little f. So how does it accelerate? What has to happen is that the horse has to push on the ground with greater force than it pulls on the cart, and that will cause it to accelerate.